So this was solid from solid. Now let's move on to, yeah, I will take your questions. Just let me cover a little, and then I will allow you to ask questions from me. I know a lot of you guys want to ask questions, and I appreciate that. Okay, now again, I'm sharing my screen with you. Okay, so yeah, so these were, now we come to solids from liquids. Solids from liquids. Now there are two types of solids, one soluble, the other insoluble. Okay, now soluble, what does the word soluble mean? Soluble means which can dissolve in liquids. Now what do you mean by dissolve? Now when we add sugar or salt in water and we stir it real well, after a time we stop absorbing the particles. I mean, the sugar disappears, the salt disappears if we keep stirring. But if you drink it, you can feel the salty taste in the water, or you can feel the sweet taste in the water. So if the sugar is still in there, which is evident from its sweet taste, why can't we see it? Where does it go? Why can't we see it? And same happens with salt, and same happens with any soluble solid. I mean, the color of the liquid might change into which you have added, but you cannot see the particles themselves. They disappear somewhere. We cannot see them. So why do you think we cannot see them? You want to try that? I want you to think. Let me ask you. Maybe you guys know. Let me ask you. Okay, Shaima, you want to answer? Why can't we see the particles that have dissolved? Yes, Shaima?
No, miss, I didn't want to say that. I wanted to say that I just joined right now. So what happened before? Did anything happen or?
No, nothing happened. I'm just talking about mixtures. I defined what a mixture is, and we discussed about different types of mixtures. I will share the slides with you. I can share the slides with you. Okay, and then yeah.
Thank you so much.
Yeah. Okay. So yeah. So where do the particles disappear? Yeah, that was the question. Anybody wants to participate? Anybody wants to try that question out? Okay, Faizan. Yes, Faizan. Yes, Faizan. No, you don't want to answer that? Yes, Abdullah.
Yes, I think so. It mixes with the particle inside the water.
Okay, but then why can't we see the particles? Why cannot we see the sugar or salt?
Because they are soluble.
Yes, yes, they are soluble, but I want you to. Okay, anybody else? Ariha? Yes.
Because they get dissolved in the water.
Yes. So what happens? What do you mean dissolve?
Meaning its taste stays there, but it's just like its particles get mixed with the water's particles.
Good job. You're very close. You're very close. And where do they go? Okay.
They're still in,
Yes.
they're still in the water.
They're still in the water. Yes. Okay. Okay. This is, I understand this is a little confusing. I'm drawing this diagram to help you visualize it in a little better way. Okay. I'm making a diagram and then I'll share my video with you. Can you open this? Okay, I'm sharing my video with you. Okay, now these are two containers. These are two containers. and they contain water. So these circles that I have made, these are water molecules. These are water molecules. Now I will add some other substance into it, such as, let's suppose, sugar. Okay. This is blue. I'm using blue color. I don't know if you can make out the difference in their colors, but yeah, I have made these dots. So these small dots are sugar molecules and these big circles are water molecules. Okay. Now, this I got wrong. Okay, anyway. So when the sugar is not dissolved, when the sugar is not dissolved, you can think of it as, you know, either existing here or here, either at the bottom, or, you know, some substances, like if you're not talking about sugar, you're talking about some other lighter substance, it might float on the surface or at the bottom. When they are at the surface or at the bottom, you can see them. They are visible to you. Your eyes can see them. Okay, because they are clustered together. They are clustered together, so they are big enough for you to see. Because, you know, after a certain size, after the particles get smaller, beyond a certain size, you stop seeing them. You cannot see them anymore. You know, like small dust particle. There are a lot of dust particles in the air, but we cannot see them. Why? Because they're too small. Well, here we can see them because they're clustered together. Now, when they dissolve, they separate into these tiny, tiny particles. When they separate into these tiny particles, they accommodate in the space between the molecules. Between the molecules, they accommodate themselves in between. So now they are so small, they're just as small as the molecule of the water itself. Okay, they are so small, they're smaller, or not smaller, but yeah, they are just as small as the molecules of water themselves. And so we stop seeing them because now they're too small for us to see, and they are separate. If they had clustered together, cluster means to group together. Okay, cluster means to group together. So when they are grouped together, so they are big enough, so we see big lumps of sugar or salt or whatever. But when they separate individually and they get accommodated in between these solvent molecules, that's when we stop seeing them, because now they are too small for our eyes. We cannot see them. So basically, the point that I'm trying to make here is that for any particle to dissolve, they have to get into the molecules. They have to get into the space between the molecules. In order for any particle to dissolve, this is very important for you to understand. For any particle to dissolve, they have to get into the space between the molecules. Okay, so that decides what solids are soluble and what solids are not. Some molecules get along with each other. They're friends with each other. And why are they friends? We will learn about that later. But for now, just know that some molecules are, you know, compatible with each other. They get along with each other. So they can very quickly can be accommodated by the water molecules, and water molecules say, hey, come on, come and join us. And they make a space for them. And so they are together, you know, just like a newcomer comes, and then the older class fellows, they take him in and he mingles and he makes friends, and then he is part of the class, just like that. But some particles, they are not friends with the water molecules. They are not friends. So water molecules do not make space for them. And so those particles stay this way. You know, the class fellows say, no, we don't want to be friends with you. And that person stays aloof. He cannot get mixed. He cannot adjust with the rest of the class fellows. So he stays like this. Okay. Sand particles. Sand particles is one example that does not dissolve in water. So they are not friends. Water will never dissolve salt, no matter what you do. No matter what you do, sand will never dissolve. Sand will always settle at the bottom. Or even if you keep stirring, you can still see the particles. It will make the water muddy. You can see the particles, but it will never disappear. Okay? So sand is one example. And then you have other examples as well, but we will deal with them later. So once you understand this, then it's easier for me to explain you further. So some solids are insoluble. So insoluble is this. Some are soluble. Soluble looks like this. This is called a solution. The one at the top is called a solution. I will write it down here. This is a solution. When the solid dissolves in water, that's called solution. When the solid does not dissolve in water like this is called a simple mixture. Okay, it's a simple mixture. I will not go into the details of the types of mixture. Okay, there are further types of mixture, but I will not confuse you. Okay, so yes. Okay, another term that I would like to introduce you to. The book doesn't talk about it, but I will talk about it because I think it's helpful. What is a mixture made up of? Simple. Solute plus solvent. Now you will ask, what are these new fancy words? Solvent is the liquid into which we add solid or anything. You know, need not be, this need not be necessarily liquid, and this need not be solid all the time. They can be any state. But for you, at your level, this is liquid and this is solid, to keep things simple. Okay? For your level, usually we are talking, I mean, examples that we will consider, solute will be solid and solvent will be liquid. But this can be any state. This can be any state. Okay? So we have two types: soluble, solute. Soluble is solution, solution. Insoluble salt, like it did not dissolve, staying at the bottom or the surface. Insoluble salt is called a mixture. Okay, you understood that? Now, after you have understood this, then it would be easier for you to understand what I'm going to talk about now. Now, the method of separating a soluble salt. I'm going to share my screen again. I'm going to share my screen. Okay, this we have already discussed: soluble salts and liquid solution, insoluble salts and liquids mixture. Okay, this is these are the methods for the of separating of different mixtures. Solids from solids, we make use of differences of size particles, simple sieving. Now, insoluble solids from liquids. Now, keeping this picture in mind of solution and mixture that I just showed you in the video, it is easy to understand that it is easy to separate an insoluble solid than to separate a soluble solid, right? Sorry, I have to switch from this to that, from this to that. Okay. I'm sharing my video. Yes. Okay, so it is easy to visualize. It is easy to visualize that it will be easier to separate this from the water, right? Because they haven't mixed. So it's easier to separate this. You know, a boy who's already aloof in a class and he does not have any friends, it's easier to change his section, right? It's easier to change his section because he already doesn't have friends. So he would be very happy to get out of that class, right? And it is difficult to take out particles which have dissolved because he has made friends. So he wouldn't like to change his section, right? So it is easier to separate this than to separate this. To separate this, we have to provide a lot of energy. We will require energy to separate particles from water which have dissolved. And this can be easily separated without anything, without any energy or heating. Now, so we will do the easy thing first. How to separate an insoluble solid from a liquid. Simple. On your page, on your book, page 27, they're talking about filtration and decanting. Filtration and decanting. These are the two methods of separating insoluble solids It can be anything, insoluble solid from water or from the liquids. Okay. Now I will show you a diagram. Now in this, okay, let me explain this book picture first. Now we're using this filter paper. Now filter paper is behaving the same way as the sieve here. It's behaving the same way as the sieve here, but the only difference is here we were separating solids from solids, and here we are separating solid from liquid. We are separating solid from liquid. Okay, and remember, insoluble solid. This is sand. Sand, I told you, it is insoluble. No matter how much you dissolve, it is insoluble. Okay, so the pores in the filter paper are only big enough to allow the water molecules to pass through. So water passes through it, is collected in a beaker or any flask, and what is left behind are sand particles, because the sand particles are too big to pass through the holes. So again, I told you, always in all the separation techniques, we are making use of the differences in their physical properties. So what difference in the physical property are we making use of here? We are making use of two physical properties, differences in two physical properties. One is, no, in fact, okay, no, we are making use of only one physical property. I'm sorry about that. So we are making use of the difference in the, again, in the size of the particles. So remember, whenever we are using filter paper, filtration, or we are making use of sieve or filtration, basically we are making use of the differences in their size of particles. Okay, and also of the fact that the sand does not dissolve in water. If it had dissolved, then this wouldn't have worked. Why? Because if it had dissolved, then it would have done this. And if it had done this, that means these molecules are also small enough to pass through the filter paper. So both the solute and the solvent will be collected in the beaker. So we cannot separate. Okay, we wouldn't be able to separate. We will not succeed in separating. Okay. Then there are some terms they have used here. This is filter funnel, you know, this conical shaped with the nozzle sticking out at the bottom. This is a filter funnel. You should know the name of this instrument. They might give you this diagram for labeling. So you should know that this is a filter funnel. This paper is called the filter paper. What is collected on the filter paper due to its bigger particles is called the residue. The term is residue. They might ask you, you know, in glossary, they might ask you to define these terms. So the sand that is left on the filter paper is known as the residue. And the liquid that is collected after filtration is called a filtrate. That's called a filtrate. Okay. And filter paper is semi-permeable. Semi-permeable. Now, what does this term mean? Semi means half. We all know that. Permeable meaning permitting. Permitting. So it is permitting some of the molecules to pass through it. It is permitting some of the molecules to pass through it. So semi-permeable. Okay. So I hope I'm clear about that. Now we come to decanting. Now, again, this is for insoluble salts. So again, they have given you this example of sand in water. Sand in water. Can you see how sand pebbles or sand particles have settled at the bottom, and therefore we can see them? Because they are not dissolving. The water molecules are not getting friends with it. So they are at the bottom. Now, because they are heavier than the water molecules, therefore they settle at the bottom. They sink at the bottom and they settle it. Now, because the water is at the top, it is very easy to pour the water out, provided the sand is settled at the bottom real calmly. You have to do this very gently, because if you will move this, some of the sand particles might rise and, you know, get suspended in the water, and so you might get some sand particles here. So if you want pure water, if you want just water, you have to do this real gently so as not to disturb the sand particles, so that the sand particles keep settled at the bottom. You understand? Okay, I will show you some images that I got from Google. Let me share with you. Maybe those images might help you. Those images might help you. Okay. Okay, this is filtration. Okay, can you see the filtrate is in the conical flask, then is the filter funnel. Okay, then you have filter paper on it. Okay, and you can see chalk, the residue is the chalk. By the way, we are separating chalk from water. We are separating chalk from water. Chalk also does not dissolve in water. So it's not friends with water. So it will stay, it is easy for us to separate it because it hasn't dissolved. So it will stay on the filter paper, and what the liquid that we obtain in the flask is simple water. Okay. So residue is chalk, filtrate is water here, and you should be able to label the filter funnel and the filter paper and the flask. Okay. Then let me show you, this is decanting. This is decanting. Again, same thing. The sediment, the sand has settled at the bottom. Okay, whatever settles at the bottom can be called sediment. Okay, that's another term. Your book hasn't mentioned it. So you won't be asked about it, I think, in the exams, but it's helpful to know that whatever does not dissolve and settles at the bottom is called a sediment. And because it is at the bottom and the liquid is at the top, we can easily pour the liquid off. Okay, this is decantation, simple. Okay, now let's move on to soluble salts dissolved in water. Now, the problem with soluble salts is that the particles are friends with the water molecule, so it is not going to be easy. It's not going to be easy. Here, this, we're talking about this. Now, in order to pull these molecules out, the ones that have made friends with water, we have to provide energy. They're not going to get out of the classroom themselves. We will have to pull them out. Okay, zabardasti. Acha lage na lage, you have to get out. Okay, whether you like it or not, you gotta leave the class. How do we do that? Now, we will use energy, which is heating. Heating, we will use heating. Now, I will, which picture should I show? Okay, let me share my screen with you. I'm sharing my screen with you. Okay. Yes. Look at this picture. Now, salt is very good friends with water. Salt and sugar, they're buddies. So the particles really dissolve really well in the water. So in order to separate them, we have to use energy in the form of heat. Okay, in the form of heat. Now, water molecules require less heat to turn into a gas. Now, the only way we can separate this salt from water is to convert one of them into a different state, into a state which will, I mean, in a state which will make it easy for us to separate them. So if we can turn water into gas, and because gases are light, they rise, that will leave the salt behind. Now, salt, on the other hand, require a lot of heat for them to turn into gas. So at room temperature, at our ordinary conditions with ordinary heating, we can only evaporate water. The water molecules will get farther away from each other and they will turn into gas, leaving the salt behind. Okay? Is that, I mean, am I making sense to you? I hope I'm making sense to you. I will let you ask questions if you do not understand anything. So I will repeat myself. So because the salt molecules are soluble in water, they are in between the water molecules. Now, in order to separate them, what we have done is we have provided energy so that the water turns into gas and evaporates. And it evaporates into gas. So we will be left with salt behind. Now, you might ask, why doesn't the salt turn into gas? Because salt molecules require more energy to turn into gas. And for that, we need to have extremely high temperature. We need to have extremely high temperature. That is not possible with our ordinary Bunsen burner or ordinary fire. I mean, you know, at room temperature. So salt has a very high boiling point. So what physical property are we making use of here? Difference in which physical property? We are making use of difference in which physical property? I want to ask you. Okay, I'm gonna give you a chance. Anybody wants to answer this question? Difference in which physical property are we making use of when we are separating salt from water by evaporation? Abdullah Musawwir, do you want to answer? Do you want to answer? Yes, Abdullah Musawwir?
Can you repeat the question?
I'm saying what difference in which physical property are we making use of in separating salt from water using evaporation?
Heat.
No, difference in their physical properties. What difference in their physical property? Like you know, I'm heating, right?
Yes.
I'm heating and water is evaporating, but salt is not. Water is evaporating, but salt is not evaporating. So what physical property difference am I using here for separation? Yes, Doris? Yes?
We are the difference in the physical form of the salt and water is that the salt needs a higher temperature to boil.
Right. Good job. Good job. So what physical property are we making use of here? Difference in which physical property? You are close. You are close. So when something evaporates, what are we talking about?
The point of
Yes, yes, yes. Yes, what? Point of?
Temperature.
Nuh-uh. Change of state. What is that point at which there is change of state? I'm giving you a hint. What is that point where there is change of state? Have you guys done a change of state from a solid to liquid to gas? Have you guys done that? No, I think that's the last chapter. You guys haven't done that.
Yes, we haven't.
Yeah, you haven't. Yeah, that's why. It's okay. It's okay. We are making, okay. I'm going to explain you. If you still do not understand, then you raise your hand. Okay. Then I'll explain again. We are making use. Okay, Shaima, you want to answer? Yes?
No, miss, I need to ask a question.
Okay.
Like, what is the meaning of desalination?
Desalination?
Yes.
Yes, okay. Desalination is this process that I'm explaining you right now. Evaporation of water, which leaves salt behind. In fancy terms, they call it desalination plants. Countries like Saudi Arabia, they use this process to get drinking and usable water from sea. Because Saudi Arabia does not have rivers and ponds and lakes and fresh water, basically, but it does have seawater and it does have a lot of oil. So using that oil, they carry out this process of evaporation. So they take seawater, they evaporate it, and because you know the temperature here is usually very high, around 40 degrees Celsius, so they don't even have to heat it. Just have lots of seawater puddles and let the sunlight do its job of evaporating the water, leaving the salt behind. And then that salt can be easily collected and, you know, purified and further processed so that we can have salt and then pure water. And that's the water that we use in our taps. Okay, usually, yeah, because we don't have rivers, so they make use of this desalination. And places where this process is carried out, it's called a desalination plant. Desalination plant, where they collect seawater, let the water evaporate, and then actually, you know, then you might ask me that, okay, when the water evaporates, how do we get liquid water? Because evaporation is gas, right? So they condense it back again. Now you will ask me, what is condensation? We haven't done the changes of the states of matter. That's a pity. You know, we should have done that chapter first. Only then you could have understood this chapter better. So, okay, let me, I have a picture here. Let me explain you a little. Let me see if I can explain this to you. Okay, first of all, let me answer that question. The question that I was asking before I forget, that what physical property, what a difference in which physical property are we making use of when we are separating water from salt by evaporation? We are making use of the differences in their boiling points. Boiling point is that physical property which we are making use of. Why? Because water has a lower boiling point of 100 degrees Celsius, whereas salt has a really high boiling point. What is the boiling point for salt? I can Google it out for you. Let me see. I don't remember. So let me Google it out for you. It must be in, it must be pretty high. I'm not getting it. Okay, so whatever the boiling point of salt is, you find out, and then you can find out yourself. It is really high. Oh, Ariha, you know it? Yes, Ariha?
It is 1465 degrees Celsius.
Wow. Did you, I mean, did you Google it out or did you read from a book? Because I want to know exact.
I have this one science book, so I read it in that last week.
Okay, good job. Good job. So I can trust you. Okay, write this down for me in the chat window.
Okay.
Write this down for me in the chat window. Okay, so that is the boiling point for salt, 1000 something. Okay, it is so high. So 110 times the boiling point of water. So we have to have lots and lots of energy to make the salt melt. So it's not going to melt at 100 degrees Celsius. At 100 degrees Celsius, only the water will evaporate. So we are making use of the difference in their boiling point. That's the difference. That's the physical property we are making use of. So whenever we are evaporating, difference in the boiling point, remember. Okay, now, yeah, I'm gonna share, look at my video. I'm going to show you something. Where did that go? Excuse me. Excuse me. Yes, okay, here. Okay. This. I don't know, this is a very messy diagram I made. I wish I could show you a better diagram. Now, these are particles arranged regularly and close together. This is a solid state, okay? When we provide it energy, the molecules move a little further apart and they lose their regular arrangement. You know, like when it's your break time. When it's your break time, you are free to leave your seats in the classroom. You can go and eat your lunch. So here the molecules are allowed to leave their seats and, you know, go here and there, chit chat with each other, you know, collide with each other, glide past each other. So this is a liquid state. And then this is gas. If we keep providing it energy, energy is required to go this way. If you keep providing it energy, the molecules get farther away from each other, farther apart from each other, so much so that there is no force of attraction between them working anymore. It's like your home time. Now you're free to leave the school. You can go home. Okay, you are not required to come back. You are not required to come back to the teacher. Same way, this is gas. Okay, this is their home time. So you are a gas when you at home time. This is solid, liquid, gas. Okay, so when this is the boiling point. Boiling point is that temperature where that exact change of state takes place from liquid to gas. And then this is melting point, is that temperature at which the substance changes its state from solid to liquid. Okay, now some substances have a very low boiling point, so it's easy, just heat it up a little and it will evaporate. And some liquids evaporate even at room temperature because absorbing energy from the surrounding is enough for them to turn into a gas. Okay, the absorbing energy from the surroundings will break the forces of attraction in between the molecules, and therefore they can turn into gas. And then condensation is the reverse process. Gas molecules coming together to turn into a liquid. Okay, in this process, this is called condensation, gas turning into liquid. And then if you further cool it down, if you further lower the temperature, the molecules get even closer together, so much so that they are regularly arranged back in their classrooms, back into solid. This is called, and that temperature at which this exact change of state takes place is called the freezing point. And remember, freezing point, melting point, same thing, same thing, same temperature. At the same temperature, you will have melting and freezing. Which one of the two takes place depending upon whether you are providing the energy or whether you are cooling it down. That will determine which way you're going. Okay, so in desalination plant, the reason why I explained you this is because I wanted to explain you the desalination. In this desalination plant, after they have evaporated, okay, like this is evaporation. So you can see the steam coming out, page 29. If you cannot see clearly in my video, look at your page 29. You can see the steam coming out of this heated water. Now this steam is gaseous in state, right? Now we want the water. For example, in Saudi Arabia, we need water. We don't have rivers and lakes. So what they do is that they collect this steam and they condense it. They collect this steam, and they condense it. So they cool it down. Okay, they make the gas pass through a cooling jacket. Okay, they have their own equipments. We're not going to get into the details of the equipments. They cool the molecules down so they come together into liquid, and that is the liquid that is available for us to use. So what do? There are two processes going on in the desalination plant. One is heating, evaporation. Why do we heat first? Why can't we just simply use the seawater? Can we just simply use the seawater? Why are we evaporating? Okay, by the way, we are evaporating so that we get pure water, because only pure water molecules will evaporate. Salt will not evaporate. Any other impurity will not evaporate. Only pure water molecules will evaporate. So when we have steam, we know we have only water molecules. We do not have anything else. So it's pure water. And so we can easily condense it without any impurity, and we are done. We have pure water. Okay, now my question is, can we use simple seawater? And if yes, why? If not, why? Yes, Abdullah Musawwir. Yes, Abdullah?
Yes, because we need the fresh water can evaporate at 100 Celsius.
No, my question is, why can't we use seawater for drinking, for bathing, for washing, or for any purpose?
Because I think it has some that what you call harmful substances in it.
Yes, there are impurities in it, and it is extremely salty, extremely salty. You ever go to beach? Try to taste it. And
I have went to beach.
You have been there, and did you taste?
Yeah, it is salty, like very much salty.
Yes, it is so salty. It is so salty that even no matter how thirsty you are, you cannot drink it. No matter how thirsty you are, you cannot drink it. In fact, they say that if, God forbid, you ever get stuck on a boat or ship in the sea and you are thirsty and there is no drinking water for you, do not drink the seawater. Do not drink the seawater. You know why? Because it is so salty that if you drink it, it will make you even more thirsty. It will not quench your thirst. It will make you even more thirsty and it will harm you. Yeah. So, yes, Furqan, you want to say something? Yes?
No,
Furqan,
teacher,
Adhar.
I want to answer the question.
Sorry?
I only wanted to answer the question.
Okay, what was your answer? I want to hear it. Okay. So yeah, so it is so salty, the seawater is so salty that even if you drink it, it is going to make you even more thirsty. So there is no point in drinking seawater. Yes, Shaima, you want to say something? Yes?
Yes, I'm saying like how will it make us more thirsty? Like
Yeah. Yeah. You know what? I can explain that to you, but then we'll be deviating away from our topic. I don't want that. I can explain that to you, but if I explain that, we will be deviating away from our topic because that is biology.
okay.
Okay? Yeah. Okay. You will learn about it, don't worry, in higher grades. You will want to learn about it. In short, if I want to say in short, basically you feel thirsty when the salt concentration in your blood rises. To be very short, I'm just trying to answer this question. When do you feel thirsty? When your blood is too salty, your brain detects it. Oh, the blood is getting too salty. And so it, makes you feel thirsty so that you drink water. When you will drink water, your blood the salt concentration in the blood will get diluted. Now, if you are drinking seawater, you are making your blood even saltier. Even saltier. You're not diluting it. So the brain does not detect it as the dilution of blood. In fact, will make you even more thirsty. Oh, the concentration of the blood has risen so much. You need to drink such lots and lots of water. And eventually, when the blood gets too concentrated, it's lethal. It's dangerous. A person can die. Okay, so they recommend do not drink seawater, no matter how thirsty you are. Do not drink seawater. Okay, now separating. Now, let's get back to, I'm sharing my screen. Let's get back to this last part, separating liquids from liquids, separating immiscible liquids. Now, when we are talking about separating liquids from liquids, where did that go? Yeah, liquids from liquids, remember, again, we are talking about the immiscible liquids. I want you to turn to page 30 of your book. Separating immiscible liquids, liquids that do not dissolve in each other. So now, just like we use the separation technique for insoluble solids from liquids, same is the case here, decanting. This, the picture that they have shown is decantation. Here, decantation. It's the same thing. Why is it the same thing? Because they are letting the two substances settle at their respective levels. Now, okay, another question for you guys. Why is the oil at the top of water? Okay, what is the meaning of immiscible? Immiscible is the same as insoluble, but we use the term immiscible when we're dealing with two liquids. Insoluble is the term that we use for solids in liquids, but because we're dealing with liquid and liquid here, so we use the word immiscible, not insoluble. Same thing as insoluble. This is the same as insoluble. Don't be confused. It's just that we are dealing with liquid. So instead of insoluble, we are using immiscible. Same thing. That cannot be mixed. that cannot be mixed with each other. That's what immiscible mean. Okay, so okay, tell me, why is the oil at the top? Oh, you know what, I forgot something. I forgot a point. What physical difference in which physical property were we using in decantation? I did not ask that question. Difference in which physical property were we using in decantation? This is also decantation, by the way. That's why I remembered that I have not discussed this with you. This is also decantation, and so we are making use of the same physical property difference. Can anybody guess? And I'm giving you a hint. It has to do with the fact that oil is at the top of water. That oil is at the top of water. Why is oil at the top of the water? Why isn't water at the top of oil? Yes, Zoris. Yes.
It's because of the density. Oil is less dense than water.
Good job. Perfect. I'm happy with you. Yes. It is the difference in the density. It is in the difference in density, because oil is less dense than water, so it settles at the bottom, at the top of water, and therefore it is less dense. And water, because it is denser than water, it settles at the bottom. So we are making use of the difference in their densities. Now, same was the case in the solid from, where did it go? Yeah, here. Same is the case here when we are separating insoluble salt, solid from liquid. Because it is denser, it settles at the bottom. And because water is less dense, so the less dense liquid stays at the top and we can easily pour it off. Now here, because we are using a different instrument, what is this called? This is called a separating funnel. Okay, look at it. You should be able to recognize it. It should be able to recognize it. This is a separating funnel. This funnel separates. So there's a nozzle at the bottom. So the liquid which is at the bottom can be decanted out. Can you see how the water is allowed to flow out? As soon as you see that I have had all water, you immediately turn off the nozzle. Okay, if you get a little lazy in doing this, you might have some oil dripping in. So you won't get pure water. So you gotta be careful. Gotta be careful while decantation, okay? So keep an eye on the levels, and as soon as the water drips out, you turn off the nozzle immediately. Okay, now, this was regarding immiscible liquids, liquids from liquids. Now, separating miscible liquids. Oh, this process I've already explained. You know, when I was explaining you this desalination, I didn't know I had this coming up. I didn't get enough time to prepare for this. So I didn't know this was coming, but this is the same thing, you know, same thing. Remember in desalination plant, I told you that we evaporate first. We evaporate first, so we make use of the difference in the boiling point. So the liquid or the substance which has a lower boiling point will evaporate, leaving the other substance behind which has a higher boiling point, right? And so same as, we're doing the exact same thing here. We're doing the exact same thing here. This is mixture of alcohol and water. But remember, here we were separating solid from liquid. So we were doing it separately, okay? We were evaporating it and then we were just condensing it separately. Here, this is liquid in liquid and they are miscible. Now I told you that the substances which dissolve in each other, it's difficult to separate them and we need to provide energy. So again, we are providing energy because they are not gonna separate just like that. Okay, they cannot separate just like that. We have to provide energy. And when we are providing energy, the substance with the lower boiling point will evaporate, turn into a gas. And then we have this instrument designed in such a way that the vapors are forced to pass through this condenser. Condenser, as the name suggests, it causes condensation. What is condensation? Condensation, gas back to liquid. Condensation. So if we want to go this way, we have to cool. we have to cool to go this way. Okay, we have to cool to go this way. So this is a cooling jacket. This is called a cooling jacket. Okay, how do they cool? Do you know? They let the cool water enter through this nozzle. They let the cool water enter through this nozzle. And when it goes inside, I mean, this is a jacket, okay? When the cool water passes through this jacket, it cools down the steam, this vapor, these vapor molecules that had entered. This cooling jacket cools those vapor molecules down. And in the process, this water gets warmed itself. This water warms up itself, turns into vapors, and then is evaporated out. So vapors out. Remember, these vapors are not these. These vapors are not the same as these. These vapors are from this cool water that you use to cool down the jacket. Okay, this is separate. Now this condenser, due to this whole process of, you know, introducing the cool water, this cool water is cooling this condenser down. Okay, and so these vapors will condense in the tube. Remember, there is a tube going in through this jacket like this. Let me draw this. My drawing is not really accurate, but you can, what the point that I'm trying to make here is that there is a tube here and the vapors are passing through this tube. Okay, and there's a jacket around it. Okay, so these vapors, due to this cool jacket, will condense and they will drip out and you can easily collect them. So what are you doing? You are evaporating. This is evaporation. And then you are condensing. This is condensation. Just writing condensation. Condensation. Okay, so this is evaporation followed by condensation. Okay, this whole process is called simple distillation. I don't know if they have mentioned it here. I don't understand why they do not introduce terms. They feel that it'll be too difficult for the students, but you know, they are explaining the whole process. The only thing they're omitting on is the name of the process. Okay, this is called simple distillation. This whole process is called simple distillation. Now, which were the two liquids we were separating? Water and alcohol. Water and alcohol. Again, we are evaporating. So we are making use of the difference in which physical property? I want you guys to answer. Evaporation, I just explained you. In evaporation, which difference in which physical property is being used? Yes, Ariha. Okay, Ariha, I'll let you answer. Yes.
The difference is in the boiling point.
Perfect. Good job. Yes, difference in the boiling point, right? Yes. So difference in the boiling point. Now, which here in this case, we are separating alcohol from water or water from alcohol, whatever. So which liquid do you think will be collected in this flask? Water or alcohol, and why? What is collected here in this flask? See, we have two liquids, right? Water and alcohol. So which vapors came out, water or alcohol? And what was collected here? I mean, of course, whatever vapors came out must be collected here because they were the ones which got condensed. So which water or alcohol is collected in flask B? Okay, Abdullah Musawwar. Yes, Abdullah?
Alcohol.
Excuse me. Yes, yes. Perfect. Yes, alcohol. Why?
Because it because alcohol boils faster than water. It has a low boiling point than water.
Perfect. Good job. Perfect. Perfect. I could hear at the background somebody saying Google से देखा है. कोई बात नहीं, Google से भी देखा है तो it's okay. It's okay. देखिए, देखने के लिए भी अकल चाहिए. ठीक है? So you have to understand. So it's okay because you are in the process of learning. It's okay to look and answer me. Okay, I want you to look and answer me. The purpose behind my asking you questions is to make you think. Because if I will keep on lecturing you non-stop, you will lose your concentration, you will lose your interest. So I want you to be active. Mentally, you should be active and keep listening to me. And your mind should keep thinking critically. So I give you questions to think about. Okay, yes, this is alcohol. Why? Because it has a lower boiling point, meaning that it will be at a lower temperature. At a lower temperature, it will boil. It will boil at a lower temperature than water. Now the water's boiling point is 100 degrees Celsius. So alcohol must be something less than 100, maybe 70, maybe 60 or around there, somewhere there. I don't remember the boiling point of alcohol, but yeah. You know the perfumes that we use, it has alcohol. So when somebody uses perfume, you can smell that person from far away. Why? Because that alcohol is using energy from the surroundings and maybe from the body of that person. And that is enough for the molecules to evaporate. And when the molecules evaporate, they reach our nostrils, our noses, and we can smell. So that shows that alcohol has a really low boiling point. So it's very easy for alcohol to evaporate. Okay, now let's do the flashbacks. Immiscible liquids do not mix well and form separate layers. Miscible liquids mix well together. So for decantation to work, we want the liquids to make separate, distinct layers. Okay, and also difference in their densities. And then it would be possible for us to separate via decantation. How do we separate miscible liquids and immiscible liquids and miscible liquids? Who's going to answer this? How do we separate immiscible liquids and miscible liquids? Miscible liquids and immiscible liquids. Who's raising hands? Who's raising hands? Easy peasy. Why aren't you guys raising hands? Yes, Zores? Yes.
For immiscible liquids, we can. It is easy because they do not mix properly.
No. My question is, how do we separate immiscible liquids and miscible liquids? Just give me the names of methods. How do we separate? Yes.
For immiscible liquids, we can use separating funnels.
Decantation. This is called decantation.
Decantation. We can use decantation.
Yes.
And filtration.
Filtration is for solid in liquids. Okay. Okay, Zores? Hello?
For miscible, we can. For miscible, we can use distillation.
Yes, good job. For miscible liquids, we can use distillation or yes, very good. And for immiscible?
We can, for immiscible, we can use
decantation.
Decantation.
Okay. Okay, another thing I want you to write down. You can see my video, right? I want you to write down here decantation. This is decantation. Same thing. You know, when we are separating using the differences in their densities and we are allowing one liquid to pour off, to come off because it has formed a separate layer, that process is called decantation. Simply separating the liquid because of the difference in their densities. Simple. Okay? That's called decantation. So whether it is for solids into liquids or liquids into liquid, both processes are called decantation. Okay, this is called simple distillation. It is a combination of evaporation and condensation. Evaporation followed by condensation. Okay, so for immiscible liquids, this simple distillation. For miscible liquids, decantation. So for immiscible, decantation. For miscible, simple distillation. Okay, clear? Okay. Is there any other flashback? Okay, this quick check. How do you separate a sugar solution which has been contaminated by sand? Oh yes, I forgot this. I forgot this page. Yes. Now, my question is now, if you have two solids dissolved in water, one is soluble and the other is insoluble. Okay, so far we dealt with soluble solid dissolving in water, insoluble solid dissolving in water. But what if we have both in the water together, but one is soluble, the other is insoluble? Then what will we do? Think, 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 think. I will give you a hint. Make use of this. Insoluble will exist like this. Soluble will exist like this. This is easier. So we will do this first, and then we will deal with the one which has dissolved. Right? So if we have two solids, okay, let me draw a diagram for you so that you can better understand. If I have two solids, these are my water molecules. Okay, if I have two solids, okay, one has dissolved in between the molecules and the other is lying on the bottom because it is insoluble. Okay, I have two. Now I have to separate. Okay, so for this, for insoluble, this I will do this first because this is easier. Okay, I don't need to provide any energy or anything. For insoluble solids, I know from my book, insoluble solids, I can use, this is insoluble solids from liquids, I can use decantation or filtration. I can use decantation or filtration. So I can use either decantation or filtration to get rid of this solid. I can use either. If I use decantation, these two molecules will be poured out into a separate container and this will be left behind. But if I use filtration, again for filtration also, this will be left on the filter paper as a residue and these two molecules will come out as the filtrate. Okay, the two molecules, the water and the soluble solid will be in filtrate. Insoluble will be on the filter paper. Okay, now how do I separate the soluble salt from the water? Soluble. Now what method did we use for separating dissolved solid? Evaporation, right? This is evaporation. We talked about evaporation. This is evaporation, simple evaporation. So first we will filter, get rid of this, and then we can evaporate. The water alone will evaporate, leaving this soluble salt behind. But in this process, we will be losing the water until and unless we condense the water somehow. Okay, otherwise we will lose the water because it will turn into gas and it will evaporate. So that is exactly what they are explaining here. Okay, separating solids with different solubilities. So one is soluble, the other is insoluble. Okay, add water to a mixture of sand and salt. Stir well to dissolve all the salt. They did not say dissolve all the sand because sand does not dissolve. So only the salt dissolved. So they dissolved, only the salt dissolved, the sand was left behind. Then we filtered the mixture using a funnel lined with a filter paper to separate the sand from the salt water. Leave the sand on the filter paper to dry. Sand is obtained. So when we filtered, the salt and water are in the filtrate, sand alone is left behind. So we have separated the sand out, but we still have salt. We still have salt. Now, how did we get rid of the water? I mean, how did we separate the salt from water? By heating it and by evaporating. Heat the beaker containing the salt water over a flame to evaporate the water. When all the water has evaporated, the salt can be obtained. Okay. I did this a little fast because we are running out of time, but I hope you understood. If not, ask me. How do you separate a sugar solution which has been contaminated by sand? Now answer this question. I want you guys to answer this question. Yes, Zores. Yes, Zores.
We can filter out the sand from the
Good job.
water. We can filter.
Yes. So if we will filter, we will separate the sand, but there is still sugar. How will we get rid of the sugar?
By desalination. We can
By evaporation.
by evaporation.
Okay, okay. Remember, desalination is only used for a seawater. I mean, it is an industrial process. It is usually used for seawater. So if we are talking about simple salt solution, use the term evaporation. Okay, so yes, your answer is correct. We will separate the sand out by filter paper, and then the sugar will be left behind, and we can separate that by simple evaporation. Good job. Now, what else is, okay, what else is left? Let me see. Okay, I think we are done. Okay, now I will take your questions. Sidra. Okay, I will now take questions from you guys. Any questions for me? Let me check the chat window. Okay. Okay, Zores, you have a question? Yes?
I wanted to tell that the boiling point of alcohol is approximately 75 degrees Celsius.
Good job. Yes. So, and water's boiling point is?
100 degrees Celsius.
Right, right. So you can very well see that how the alcohol will evaporate first because it has a lower boiling point, because we will achieve 75 degrees Celsius before 100 degrees Celsius. And also, I did not mention this point, that you have to raise the temperature gradually. Okay, you have to raise the temperature. I mean, okay, I'm talking about this. I'm talking about this page 30, that you have to, when you are heating, can you see there's a thermometer here? I did not talk about the thermometer, by the way. When we are heating, we have to heat gradually. Gradually, meaning we have to start from lower temperature, real low temperature, well below the boiling points of both the liquids. So we should know the boiling points of both the liquids beforehand, and we will start warming. And remember, our starting temperature should be well below the boiling point of both the liquids. Otherwise, they will be evaporating already. Okay, and then this thermometer is so that we can regulate the temperature. Okay, this thermometer has more functions as well, but for now, for you guys, just remember that this thermometer is so that we know which liquid is coming out. Okay, so when we have 75 degrees Celsius, when the mercury hits 75 degrees Celsius in this thermometer, we know that the vapors coming out are of alcohol, not of water. Okay, not 100%, this is not 100%, but yes, most of the vapors are of alcohol. Okay, and the liquid has water. The liquid has water and the vapors are of alcohol. So we know that the vapors that we are collecting are of alcohol. Now, when the mercury hits 100 degrees Celsius in the thermometer, then at that point, the vapors coming out would be water. And at that time, because we don't want the water to mix in the alcohol, we will disconnect this. We will disconnect this because we don't want the water to contaminate the alcohol, or we don't want the water to mix in alcohol. Okay, because we want separate. Okay. Any other question? Zores, do you have more question? Yes.
I also wanted to say that we can also use a condenser to liquefy oxygen.
Yes, yes, we can use container to liquefy a lot of things. Yes. Any other question?
No.
Okay,
Thank
good
you.
job. Okay, Ariha, I'll take question from you. Yes?
I just want to tell you the boiling point of alcohol.
Oh, okay, okay. So yeah, now we
Exact
know.
boiling point.
Okay, okay. So, okay, so are we guys all clear about this?
Yes.
Yes.
Okay, okay. I would recommend that you guys read the chapter before the class and read that same chapter again after the class.
Okay.
So, I mean, why before? Yeah, and then that way you will understand the chapter really well. Okay? Okay, so I'm now ending the meeting. If you have any question, then yeah, okay. A couple of students. Okay, a couple of the students have complained that I can read in the chat window that they did not get the message. Yes, you know what? I was not sure if I'm taking this class because of the school online classes. The school has also started online classes, so I did not want to overburden the students, and I was not sure if you guys still want a class or not. That's why I did not mention. I mean, I did not remind yesterday, but then and then I know all of a sudden I decided that okay, I will, because most of you are done with your online classes by 12 o'clock, so it's okay, and you get a 1 hour break, so I can start a class at 1 p.m. But if you want me to change the time or anything, you can let me know. Okay, and I cannot message privately because there are so many students out there. It's not possible for me to inform everybody privately. I usually inform in 5A group because my daughter is in 5A, and I also inform in the general grade 5 group. Okay, so if you guys are in one of these groups, it would be easier for you to get get to know about my timings. But for now, my timings are Wednesday 1 till 2 p.m. Okay, Wednesday, every Wednesday, I'm writing it down in the chat window. Every Wednesday from 1 p.m. till 2 p.m. Yeah, and then I can extend it a few minutes more if I feel the need in questioning and answering your questions, so it might last for 2:30 or something. But yeah, at till 2 p.m. I'll try my best to finish off with my lecture, okay, with my explanation. Okay, so every Wednesday from 1 p.m. till 2 p.m. Okay, I have messaged in the chat. Okay, and I have also mentioned this in the two groups that I have talked about in 5A and also in a general grade 5 group. Okay, so okay, Allah Hafiz.
Allah Hafiz.
Allah Hafiz. Allah Hafiz. Assalamu alaikum.
Allah Hafiz.
Allah.
Allah Hafiz.
Allah.